Hello everyone, my name is Steven and I'm currently a human bio major at USC. And today I'm going to be talking about the physics of the eye and how it relates to what we've been learning so far in class in terms of converging and diverging lenses. So let's get into it. So first let's talk about the anatomy of the eye. So here I have a hand-drawn picture of the eye and here is the cornea. And the cornea is responsible for two-thirds of the power of the eye. So two-thirds power. And then this is the lens, this yellow part. This is the lens. And it's responsible for the rest of the power of the eye. And the reason that these two or parts of the eye is so powerful is because they have fairly high index of refraction. For example, the cornea has an N value of 1.38, which means that it is fairly capable in bending light away from its original path. So now that we have the anatomy of the eye sorted out, let's talk about how an image can be translated from reality to our brains. And for that is that the light rays from the object gets gets sent to our eye, and then it bends, it converges, and then eventually it will lead to a projection of the image on the back of our eye, as you can see. So let's talk about how it bends in order to project the image. So let's take an example for here. We have a button, and then I'm just going to draw the axis, just like how we've been seeing it in class so far. And then we have our eye right here. For simplicity reason, I'll just act that this part right here is just one, lens, so that I don't have to draw two little bends because it's very complicated on the iPad. So let's just take what we've been learning in class so far. So first, let's take a parallel ray from the top of the object, and then it's going to refract this way, okay? And then let's take another light ray that goes through the center of oh, that is not right. Goes through the center of the said lens and then hits also the back. And it should match up. This is the focus point right here, as we all know. So right here, this is F, right there. And then right here is the upside down image of our button, right there. And you can simply replace the um, image with an arrow. So for example, let's just use the arrow to indicate orientation. As you can see, the magnitude is in the negative because it's flipped upside down. So as you can see, very similar to what we've been learning in class so far in terms of lenses. It's just that simply our eye has two lenses and bends the rays twice. But in the end, it's still the same result. Also, we can also draw a third ray. So there's a parallel line that goes all the way here. And when we trace it all the way to the top of the object, this is also the focus. The length over here is the same as the length here. So as you can see, these three rays are the rays that we learned in class so far, and they do correlate back and forth. So in our book basically calls this a case one scenario in which an image is formed by a single thin lens. And this is because this right here acts like a convex lens. The focus is greater than 0. It's positive, which means, and as you can see, the object distance is longer than the focus distance. And also, in addition to that, we have a positive image distance, and also this is considered real, since all the light rays do actually, if they're not imaginary light rays, they're actually light rays that converge at this point. And also there is a negative M, as I've said before, since it's upside down. So now you may be asking yourself, wouldn't the object distance have to be the exact same for every time so that an image is projected perfectly right at the back of the head, the eye? And that is a great question because the lens actually can change the shape based off of the pupils right here. And by changing the lens shape, they can refract the rays differently so that a perfect image is projected onto the back of the eyes. Yeah, so all in all, I hope you guys learned a thing or two about eyes and how our eyes work. So, yeah, thank you for watching this.